My name is Thatcher Chamberlin, and I wrote a package called TinyEKFGen.jl. It's for generating Kalman filters that I, in particular, use on a satellite, but it's very general for a lot of things. So this is this new package. I actually tried to register it earlier this week, so I think it's in the CI pipeline right now. So maybe by the end of the talk, you'll be able to download it. I'd just like to tell you a bit about it today. So I want to go through a little background on EKFs, what these extended Kalman filters are, why I in particular wanted one, how I found this one called TinyEKF. That's actually a C library that I'm using, and then how Julia and symbolics factors into that, and maybe a little demo at the end. So I work at a company called Link. We're a satellite company. And when I joined a couple of years ago, we needed to make a spacecraft attitude determination system. So you have these sensors, magnetometers, gyros, kind of want to fuse them into like an orientation estimate of the satellite. Kind of not trivial to do. You can't measure it straight off without like a star tracker, which we didn't want to use at first. But this extended Kalman filter is a sort of a structure that'll let you do this kind of thing really easily. You can use these EKFs for a number of things. One is state estimation just in general. Doesn't really work on problems with hard constraints, but in general, if you can have something that has a nice, smooth, like differential equation, you should be all set. It's used a lot in drones, so if you have a quadcopter or a little airplane, definitely has an EKF in it. It's pretty standard for satellites, so you'll see them there. GPS chips use EKFs inside to figure out your position from pseudo ranges from the GPS constellation. And kind of anytime you see sensor fusion, there's an EKF or similar thing there. The EKF is actually like the non-linear version of just this thing called the regular Kalman filter. It's a recursive linear filter used for estimating a state from noisy measurements in a system model. So you need to have a model of your system, differential equation would work. And then you're going to be taking some noisy measurements and updating your state from them. You're just going to have this estimated future state that you'll get from your current estimated state and some measurements and a vector h. Then you're also going to need a state transition matrix, call that big F, and a matrix that relates your state to these observations that you'll be taking. So in my case, that might be what I think a magnetic field might be from a certain orientation that I'm in. There's also these noise matrices. I'm not going to really touch on them here, but they're called Q and R, and they describe how much noise is going to be present in your observations and in your state model. And if you have all these things, you get them together, you feed in measurements. This estimated state should converge on the real state that you can't actually measure. Extended Kalman filters are an extension of the Kalman filter. Same equation, same process. The main difference is these constant matrices, F and H, are now functions of your state. So things are no longer linear. There's not the same guarantees the Kalman filter has. And we're going to have to recompute these matrices on each step of the filter. In our cases here, big F is actually the derivative with respect to the current state of the future state, and big H is the derivative with respect to the current state of the predicted measurements. So for the situation I was in, I decided this is going to work, put this on a satellite. The other constraints I had in this project were the need for compatibility with C programs. That's what we run. Can't be allocating memory, so C is pretty good for that. At the time, I was the only one working on the project, so had to use time effectively and didn't want to be writing out huge matrix products in C. That'd be a lot of time. Also, odds are I wouldn't get it right the first time, so I wanted to be able to iterate quickly on different kind of models that I might encounter. I found a good way to do this was TinyEKF. This is a C library from someone named Simon Levy. It's on GitHub. It's great. It's MIT licensed, so easy to use. It's actually designed to run on like Arduino microcontrollers, so very lightweight. I wanted to run this on a Linux computer, so should be no problem in terms of resources. He mostly used it for quadcopters, so I think that should work well for the satellites. The one issue here is if I want to use this in C, you have to populate the entries of these matrices, big H and big F, and there's a lot of entries. Here I'm just showing the non-zero ones, but the matrices are like 18 by 18, and they're pretty, they got a lot going on in there. Wouldn't want to write it out by hand, probably make a mistake. So we're going to use Julia and symbolics to kind of emit this code for us, compile it into the C, and then good to go. Yeah, so the plan is get Julia to generate this C code for us for these big matrices. I've been using Julia. I actually learned it in a linear algebra class here, which is kind of fun. And I was also struck by the symbolic programming capabilities that seemed pretty great. Other options that we were exploring at the time were MATLAB, Mathematica, and Octave, but it's a lot harder to run those in CI and on the satellites if we wanted to. I'd also used SCM utils before. I don't know if anyone's seen that, but it's in Scheme, which is cool, but hard to use. And I was also intrigued by, at the time, the multiple backends for the symbolic stuff. So I ended up using SymEngine. If I was doing this again today, I'd like to do it in symbolics. So that might be some future work. I can't say too much about how this worked, but it did work. It's really cool. It's flying in space. With data, having run this a bit, we were able to refine the EKF over time and change the code gen a bit, and it continues to work. This was originally a Pluto notebook that I just had on my computer, but now I've cleaned it up, put it into a module, and now it's a package, and call it TinyEKFGen.jl. This is kind of the flow. You have really nice symbolic code in Julia, just abstract, and you don't need to know that these are vectors or matrices or anything. And then you can get out this very complicated but accurate C code, kind of as much as you like, any size state. You don't have to worry about it. Cool. So I have a bit of a demo here. I think we should have time. I just want to run through kind of how this might work in a kind of toy example. If we could imagine a ball tossed in the air, it's going to be a nice parabola. So we'll imagine a situation where we have some noisy estimates of its position. Maybe we want to back out what its velocity is from that. So if you were to do that, you can just install these libraries. And as a lot of things I've seen this week, we're going to start off defining a few symbolic variables. Next up, we need to tell the filter what our state vector is going to be. In this case, we'll say we want to estimate the position and velocity of this ball in the air over time. So very nice, just Rx, Ry, Vx, Vy. We also need to do the evolution. So if we know the state now, with kinematics, we can work out what the state will be, dt in the future. It's all a little messy, but you expect the position to get a bump of the velocity, and your vertical is going to have a 1/2 at squared for acceleration due to gravity, and your velocity will change a little bit. The observation model is, we'll just do a very simple one to start. If we have time, we'll come back and look at this. But we could say we have a little GPS, and we can actually measure the position of this ball over time. But note that we're not measuring the velocity. We're going to sort of pull that out of the filter later. It's very simple. Little measurement here, just the position vector. Also to show that this is actually an expression we can evaluate. So, if we sub in dummy values for all these variables, we can see that our second predicted observation is what I put in for the y position. Okay, so that's actually all we need right there. I'm going to define acceleration due to gravity to be a constant, give it a 9.81. And then this is the call to the TinyEKFGen package. Just need to give it the current state, future state, predicted observations, and any constants that we might want to have in our expressions. This is going to populate a file of our choosing with this function model. And it's very quick. It'll do all the derivatives for us. We can take a look at that right here. Okay. So this is pretty nice. These actually aren't too complicated. You could probably do this by hand. And if you're careful checking it, you'd probably get it right. Good to check. So we expect our predicted observations, if we take the derivative of that with respect to our state, we should get this kind of 2x4 matrix with ones on the diagonal. And we do actually get that. Everything not shown here is 0. So that's looking good. I have this little C program I wrote by hand. It's kind of long, but it doesn't do a whole lot. It's just going to initialize one of these EKF structs from the TinyEKF library I'm using, take some noise parameters from CLI, read in a bunch of CSV measurements, and then call that model function that Julia wrote before doing the EKF step call, which is again from the C library. Yeah, I don't think we'll really read through all of this, but it's there. The last thing we need quick is some kind of dummy measurements. So I have these pre-computed, just the trajectory of a ball through space. I'm going to load that in. And then here, I want to take our predicted observations from before and apply them to each row of my simulated data. So in this case, all we're doing is pulling out X and Y position, adding some noise, and we're going to save this orange line to a file, pass it into the C function. Yep, we're just going to save that out there. And then finally, we get to run it. So this already ran, but I can run it again just now. It's very quick. So we're going to make our parabola C program, run it on our noisy measurements, save it out to here, and I'm also passing in the variance of the measurements that I expect. That's going to make a EKF result file, and we could read that right here. Cool. So this has kind of unsurprisingly worked. We just gave it position, and you see there's kind of these error bars. Another feature of these filters is they give you a good sense of your error in your estimates. And they converge pretty nicely over 10 seconds. It takes a while for it to figure out the velocity, but even without any velocity measurements, it's able to do that. It's kind of a standard feature of these filters. So nice to see. I would say this worked. I was able to use C, which is kind of my constraint going in. I was able to write this by myself pretty quick, but it's unclear from this demo, how quickly you could iterate. But I think we have time to see that. So I kind of want to do this again, but I'm going to actually change the observation model. So at first, my observations are very simple. Just position and velocity, or just position. going to change that to these new measurements. This is kind of range, magnitude of position, and this is, I think, range rate. So this might be analogous to if you had a radar, and you could ping something, see how far away it is, see how fast it's moving towards you, but you don't have any sense of angularly where it is. We'll see if we can still get the velocity out of that. Okay, so our measurements are a lot more complicated now. I wouldn't really want to take the derivative of this myself. I think you could, but take a while. And we can still evaluate this. It's a lot less trivial to check that that's right, but I think it is. We're going to do the same thing here. So with this new model, we can run the generation again. There it is. Took a little longer. And let me reload the code. Okay. It's done that as well. This is a lot harder now. Really wouldn't want to write this in C. Really keeps going for a while. But that's what we want. And if you'd like to confirm, the entries of H here should match this matrix. That's our derivative. And for now, we're just going to trust that that's correct. Okay, same thing as before, same program. This needs no updating. As long as we feed it the right model and the corresponding measurements, we're all set. Speaking of measurements, we have the same, input state, but our measurements are now a lot stranger. So this is, again, it's the distance from some observer and like the range rate. So before it was a nice parabola. You could probably eyeball what the velocities are. This, it's a lot less clear of what this particle that we're tracking is doing. So this is a more interesting example of the filter. So we save those out, compile it, give it a quick run, and I should have shown it before, but so it does converge towards the end. We're still able to estimate the 2D velocity of this particle from range and range rate. The error bars are a lot higher this time around. I think there's kind of a singularity in the middle where it's not really able to estimate well. But towards the end of this range, it does converge really nicely on the true state. We're trying to converge on the orange line and on this kind of light blue. So, it's uncertain in the middle, but gets there towards the end. Yeah, so this is something you can iterate pretty quickly. If you had a different system model, maybe you want to add like air resistance or drag, you could pretty easily add that in symbolically as well. So I'm very happy with this. We got these matrices, 2 different kind of measurements very quickly, and no math by hand. Cool. So the state of the package is I was hoping it'd be released by now. I sent it on Monday, so maybe by sometime today it'll be available on GitHub, or it's on GitHub now, might be in the general registry soon. It's still pretty in work. This has been an internal tool for a while, and it's just going out into public, so it's pretty specific to our use case at the moment, but it does work in space, so I'm pretty convinced by that. It's very possible that if you tried to run it on an aircraft or a chemical reactor, there's some edge case that we could find that maybe it needs a little work. There's definitely features to add too. I'd like to add these noise matrices, which have sort of been skipped over here, but they can also involve some pretty big derivatives. I'd also like to replace the SimEngine dependency with symbolics. I don't remember why SimEngine was the way I went in the first place, but symbolics seems really fun these days. The trick is maintaining back compatibility. Since we do use this on a kind of critical system, we need to keep it that way. I also have my own code gen in here. I know Symbolics has a C code gen as well. Might make sense to use that. And instead of emitting an H file, we could emit C or .o files and maybe do more kind of unit testing with C-call. I don't know how well you can see this, but this Q matrix, which I've assumed is constant, is generally not. So I'd like to kind of dynamically generate those as well. Finally, I've really enjoyed using the TinyEKF C package, but I think that need not be a requirement in the future. It could be that we code gen the entire EKF code as well from Julia, which would be kind of neat. And that's actually all I got. I think I finished up a little early here, but I'd be happy to turn it over to questions if there are any. Thanks.
Thank you very much. Questions? There we go.
You mentioned symbolics. Do you have any plans to like plug this into modeling toolkit to take models that people have already written for their plant kind of and use that or anything similar? Wait.
So the question was, I mentioned symbolics. Do I have plans to integrate with modeling toolkit and run systems from there as well? No, but that's a good idea. I've looked at modeling toolkit a little bit for other projects, but I hadn't considered it for this. I think it would make a lot of sense.